Good evening. Let us solve this question number 7.5 from the gravitation. In this question, they are asking, let us assume that our galaxy consists of 2.5 into 10 power 11 stars, and each one of each of one solar mass. How long how long will a star at a distance of 50,000 light year from the galaxy center take to complete one revolution? So let us assume that there is a galaxy. Okay, see, actually the galaxy may be like this, maybe spiral shape, but here we need to assume that galaxy is in a spherical shape, and it is consist of a several stars. So many stars are there in a galaxies, like this, like this, like this, like this. So many stars are there, right? Okay. Now, how long it will take? Will a star at a distance of 50,000 light year? So basically we need to find a time period. We need to find a time period. Okay, is equal to what? Now first of all, if we want to find the radius of the galaxy, so how you will find radius of the galaxy? Radius of galaxy. So in this here they have taken that, take the diameter of the Milky Way galaxy to be 10 over 5. So radius of the galaxy will be 10 over 5 light year divided by 2. So this will be 5 into 10 over 4 light year. Okay, so which is exactly uh, about this 50 c here, which is exactly equal to this. It means that we want to find the time period which is just at the circumference, or at the end, or at the sphere, last end of the sphere, spherical shape of the galaxy. Okay, so let us consider this is the area where our stars is there, and we need to find a time period for this. Okay, now if we want to convert it into meter, so we have to do some of the calculation. What type of calculation we need to do? See here, it is in light year, so if I want to convert it into light year into the meter, so just I have to multiply it by 5 into 10 to the power 4 into 9.46 into 10 to the power 15 meter. So finally we will get 4.73 into 10 to the power 20 meter. Okay, now we need to find a mass of the galaxy first of all. Since here they have written that, let us assume that our galaxy consists of a 2.5 into 10 power 11 stars, each of one solar mass. So the mass of the galaxy, I want to find the mass of the galaxy. So how I will find mass of galaxy is equal to number of stars in a galaxy, that is equal to 2.5 into 10 power 11 into mass of each star, that is each star is equal to one solar mass, that is mass of the sun. So we know that the sun mass is equal to 2.0 into 10 power 30 kg. So finally we will get mass as 5.0 into 10 power 41 kg. Now as we as a whole, can we think that the whole mass appears to be the center? So center, it can be considered as a point mass, and this whole star is moving in a circular way. So if I will consider in a point mass, so one equation will be one equation that is equal to m omega square into radius is equal to g capital M small m by r square, we can write this. So m got cancelled out, and omega, we know that omega is equal to 2 pi by t. Just we can put here time period, omega is equal to 2 pi by t whole square is equal to g into capital M by r cube. So from here we can find that time period t is equal to 2 pi root under r cube by g into m. If we put the values of all these things, so what we can get, r cube, that is r cube means radius of the galaxy, that is equal to 4.73 into 10 power 20 whole cube divided by g. What is the value of g? G has a value 6.67 into 10 power minus 11 into m, mass of the sun is m, is equal to 5 into 10 power 41. So when we calculate this, we will get the time period t as 1.12 into 10 to the power 16 second. If we want to convert it into day, so let us consider it into year. If I will convert it into year, so we will get 3.5 into 10 to the power 11 year. I hope you have understood this question. In this question, they're telling that choose the correct alternative. First is, if the zero potential energy is at infinity, the total energy of an orbiting satellite is negative of its kinetic or potential energy. So let us consider from at any point at infinity there is potential energy is 0. Okay. Now if potential energy is 0, which, and now the at this distance, at r distance, the potential energy U is equal to minus G into capital M minus G into capital M into small m by r. Now if I want to find kinetic energy, so kinetic energy is equal to half into m into v square. Now what is v? So as we know that velocity v is equal to root under g m by r. Why this happens? Because we know that if anything is rotating around a circular path, so what will happen? mv square by r will be equal to g m into small m by r square. So from here we can get velocity v as a root under gm by r. So when we put here, so what will happen? Half into m into v square means gm by r. So finally we will get half g into capital M small m by r. So when we talk about total energy, so total energy will be minus gm into small m by r plus half g capital M small m by r. So this is equal to, total energy is equal to half into minus half into g into capital M small m by r. So this is negative. So definitely this is a potential energy, the expression for the potential energy. So our answer will be that if the zero potential energy is at infinity, the total energy of the orbiting satellite is negative of its kinetic energy and potential energy. So the won't be kinetic energy, it will be potential energy. Now another question is there, another question, that is B part. B part question, they are asking that the energy required to launch an orbiting satellite out of the Earth's gravitational influence is more or less than the energy required to project the stationary object at the same height. See here. Let us consider this is the Earth and there is an orbiting satellite. It is moving. Okay. And there is an stationary object. Or so the energy required to launch or project will be equal to gmm by r. This will be the amount of energy. But when we talk about the orbiting satellite, so it has already a kinetic energy. So the total energy required to push or energy required to launch will be less for the orbiting orbiting satellite. So the energy required to launch the orbiting satellite out of the Earth's gravitational influence is less than the energy required for the project stationary object, because in a stationary object you don't have a kinetic energy, so kinetic energy is already equal to 0, so maximum energy you have to put in the effort. Now let us see the question number 7.7 of the gravitational chapter. Does the escape speed of the body from the Earth depends on the mass? So first they are asking about the mass, or it depend upon the location from where it is projected, or the direction, or the height. So let us see here. Let us consider this is the Earth. Okay. And there is an object which is placed on the Earth. So the potential energy of the Earth is gm into small m by r, and this will be negative. Now this energy has made this object to be stable here only, so we have to put this amount of energy so that it can just go out. So minimum minimum energy we have to put, so we can give only the minimum energy in the form of kinetic energy. So let us consider this kinetic energy as a half mv square, and this must be equal to 0, so that total mechanical energy will be 0. So total energy will be 0, so they will this object will get escaped out. So if small m will get cancelled out, so what we will get here, so v square is equal to 2 g into capital M by r, 2 gm by capital R. Okay, so v will be equal to root under 2 g into small m by r, where r is the radius of the Earth. If I will multiply and divide by r, so what we will get? We will get root under gm by r square into 2r. So this value we will get as a small g, that is gravity. So 2g into r. This is the general formula. Okay. Now the question they are asking that what is at which entity this depends upon. So from here we can see that it does not depend upon the mass of the body. As there we have got the cancellation. So the first option will be wrong. That is, it does not depend upon the mass of the body. Second, location. So it does not depend upon location either. You can keep object anywhere on the Earth surface, so it will not depend upon the location. Now third one, that is C option, is the direction of the projection. So it does not depend in which direction you are just throwing it, just perpendicularly or just at this angle. So it also does not depend upon the direction of the projection, because we have got this type of expression where no directions are required. Now at the same time they are taking about the height. So let us consider an object has been placed at a height h. So if it is a height h, so what will happen? R will increase. If R will increase, then what will happen? If R will increase, then what will happen? So if R will increase, see here, ultimately we have got this. If R will increase, so velocity will decrease. So finally, velocity will decrease means kinetic energy less is required. So it is dependent on the radius, height. So the final option, that is D, is the correct one. So it depends upon D. Hence our answer will should be, it depends upon height of the location. Now, question number 7.8 for the gravitational chapter. A comet orbits the sun in a highly elliptical orbit. So let us consider there is a sun, and there is a comet which moves in a elliptical orbit. So let us consider there is a comet here, so which will move, right? Okay. Does the comet have a constant linear speed? So first question they are asking, does the comet have a constant linear speed? Constant linear speed. So as we know that angular momentum will be conserved. Angular momentum will be conserved, as we know that angular momentum, that is L is equal to mvr, will be conserved. So at the moment, each and every area you can find that radius is different. So if r will increase, so since as linear angular momentum is conserved, so velocity has to decrease. Here r is decreasing, so velocity is increasing. It means that our conclusion is that velocity will vary. I hope you have understood now. Now B, angular speed. A, linear speed, angular speed. So we know that angular speed omega is equal to v by r. So velocity is also changing, r is also changing. So sometime velocity is increasing, r is decreasing. So omega will also change. Okay. Now let us talk about C, angular momentum. So L will always be a constant. So it will always be constant. Now D is your kinetic energy. So kinetic energy, what is kinetic energy? Half mv square. So what happened? V will change, V will increase, V will decrease. So kinetic energy will also be variable. So kinetic energy will also change. Now about E, it is potential energy. So potential energy will, whatever potential energy, so potential energy will also change. It will also change due to change in a distance, due to change in a r, change in r. Now fifth one, that is they are asking, is that total energy throughout orbit will change? So total energy throughout the orbit will remain constant because gravitational energy is conservative. Gravitational energy is conservative. Okay, so this will remain constant. I hope you all have understood this section. Now this is question number 7.9 of the gravitational chapter of the NCERT. Which of the following symptoms is likely to afflict an astronaut in a space? Let us consider this is an astronaut. Okay, this is an astronaut. I'm not good at a drawing, so please. This is an astronaut. Okay, now it is totally covered. Everywhere it is covered. Everywhere it is covered. Okay. Now see here. Which of the following symptoms? It means that astronaut will face different type of problem. So first, A, swollen feet. Since here, see, swollen means what? If see here, when we walk, when there will be more gravity, when there will be gravity will be very high, so what will happen? Most of the blood in our feet will come, so it will create a swollen. Okay, it will create a swollen. But as we see that when astronaut goes above, so gravity is very less. Gravity is very less. So if gravity is very less, so what will happen? Blood will not accumulate at the feet. So what will happen? There will be no swollen feet. So I think A is the incorrect symptoms. Now let us talk about the B one. A is incorrect. Uh, B is swollen face. See here, if there is a very high gravity, so what will happen? Most of the blood pressure is high at the feet and low at face. But when there will be no gravity, so what will happen? Blood will flow at the face. So if blood will flow at the face, so what will happen? There will be a very high blood pressure. Due to high blood pressure, what will happen? Face will swallow. So SWOW, swollen face is the correct one. Now let us talk about the headache. Since blood pressure, since BP is high, so normally what will happen? Headache will be there. So these are the symptoms. Now the orientation problem. So this is very important. Orientation means what? See here, in earth what will happen? The gravity is always acting downward. So what will happen? You will think that which direction we are going, which direction not. So we have no orientation problem. But at the space, what happen? No gravity is there. No gravity is there. So no orientation. So there will be an orientation problem. There will be an orientational problem. I hope you have understood this. So this will happen, this will happen, this will happen, but this won't happen. So A is the incorrect one, B, C and D is the correct one. So I hope you have understood this.